Hello there and welcome to this online workshop all about understanding molecular orbitals and orbital hybridisation. I'm Dr. Tom Robshaw. So this series of video workshops is designed to help the transition of foundation year and first year students into chemistry focused modules, people who maybe don't have a strong previous background in chemistry. You'll need around 15 to 20 minutes to complete this video workshop. There are a number of quick practice questions throughout. At these points you can pause the workshop and work through the questions at your own pace. To get the most out of this session, you'll need a periodic table and something to write or draw with. A periodic table can be downloaded using the link in the comments. So let's just quickly go through the learning objectives for this session. You're going to learn how to explain why molecular hybridisation occurs in molecular orbitals. We'll introduce the shapes of different types of hybridised molecular orbitals. sp3, sp2 and sp. You'll learn to recognise them all. We'll look at the differences between what's known as a sigma covalent bond and a pi covalent bond. And by the end of this, I hope that you'll be able to identify the hybridisation that is going to exist in the molecular orbitals with respect to any given atom in a simple organic molecule. So this is very much a follow-on video, a companion video to the one that I did on chemical bonding and atomic orbitals. If you haven't watched that video yet, I advise you to go back and engage with it before you try and understand this one, because it will help with your comprehension a lot. Anyway, by the end of that video, we had got as far as constructing a very simple atomic orbital energy diagram for some of the simpler elements, showing their electron configurations, their electron subshells and their electron orbitals. Now, having understood atomic orbitals, we're now in a position where we can tackle molecular orbitals, and in particular the concept of orbital hybridisation. This is where people begin to have problems usually. It's important not to become intimidated by that word hybridisation. It sounds big and scary. All it means is mixing together of two different things so that the end product has some of the characteristics of both. So if you think of a hybrid car like this one on the left, it has both a petrol engine and a battery. It has properties of both. And on the right I found what I'm pretty sure is a fake picture of a liger, which is obviously a hybrid of a tiger and a lion, but same concept. Right, let's go back to the example of methane, which we met in the previous slide. Methane is one carbon atom bonded to 4 hydrogens. CH4 is its molecular formula. Now, if we were to take the existing atomic orbital configuration from the central carbon atom and then add in the 4 shared electrons from the 4 hydrogens, to complete the carbon's octet, remember octet equals 8 electrons equals full outer electron shell, you can see that the diagram would look something like this. The electrons from the hydrogen, from the 4 hydrogens, are shown in red. But I hope you can see that clearly this can't be right, because according to the diagram, in the valence electron shell, which is the second shell, the shell that's actually involved in the chemical bonding, we've got hydrogen and carbon electrons at all different energy levels. We've got 2 hydrogen electrons. We've also got 2 hydrogen electrons in one orbital, the 2pz orbital, which is nonsensical. The hydrogen atoms don't bond with each other, they bond with the carbon. All the carbon to hydrogen covalent bonds in methane are exactly the same energy as each other. We say they are degenerate. So the model has fallen apart. Something needs to happen to equalize the energies so that all covalent bonds are the same. And that something that happens is hybridisation. What happens is that we take all of the bonding electrons from the carbon, so all the electrons in the second electron shell, the valence shell. The first shell, as we see at the bottom here, doesn't take part in the bonding at all. It just stays on its own. So we take all of those and all of the bonding electrons from the 4 hydrogens, mix them all together, and what comes out, as we see in the middle, are 4 hybrid degenerate molecular orbitals. They have some 1s character from the hydrogens, some 2s and some 2p character from the carbon, and they're all at the same energy level. Because they have a mix of s and p character, their shape is somewhere in between the s and p shape, as we see here. So it's not a perfect peanut like a p orbital is, it's kind of a lopsided peanut. This specific type of hybridization is called sp3 hybridization, and all carbons that have 4 single covalent bonds going to other atoms will feature this sp3 hybridization. These single covalent bonds have a special name. They're called sigma bonds. This is at the bottom you can see the Greek letter for sigma. Once double and triple bonds start to get involved, things become more complicated, and we can't really use our simple orbital energy level diagrams anymore. The model just does not describe the bonding properly. It becomes more about just remembering a few facts. So let's look at the simplest molecule with a double bond possible. Let's look at ethene. Now each carbon in ethene is bonded to 3 other atoms. It has single bonds with 2 hydrogens and a double bond with the other carbon. For each carbon we have 4 pairs of electrons involved in the bonding. Now 3 of those pairs are hybridized and degenerate, and they are called sp2 hybridized, and overall it's an sp2 hybridized carbon. These pairs form the bonds between the carbon and the hydrogens, and one of the bonds between the carbons. It's completely arbitrary. Let's say it's this bottom one here. Any carbon that bonds to 3 other atoms in total is sp2 hybridized. You can see that compared to sp3 hybridization, there's a little more s character and a little less p character in the molecular orbitals. The peanut has become a little bit more lopsided. And again, these are all sigma bonds, the ones that I've just described. There is a special case for the last pair of electrons. These electrons remain unhybridized, and as you can see, they mix in a different way and make a different molecular orbital shape. Because of this, they form not a sigma bond, but a pi bond. Again, it's a Greek letter, pi. Here it is here, pi. Remember the alliteration. You need p orbitals to make a pi bond. Pi bonds have some important characteristics. They're higher in energy, weaker, and easier to break than sigma bonds. And this is the reason why organic species with double bonds are generally chemically more reactive than similar species with single bonds. This is the driving force behind a number of biochemical processes, steps in drug synthesis, and other important organic reactions. The last type of carbon hybridization you need to know about is sp hybridization. This happens when a carbon is bonded to only 2 other atoms, and this is actually quite rare in chemistry. The only common example of this is with alkynes, species with a triple carbon-to-carbon bond, and the simplest one is ethine here. Each carbon makes 2 sigma bonds with hybridized molecular orbitals with a hydrogen and with the other carbon. Those bonds are shown in orange here. This time we have 2 pairs of unhybridized electrons left over, and these make up 2 pi bonds between the carbons. Again, with the hybridized molecular orbitals, because of the decrease in p character, the hybridized orbitals have more s character than in ethene and look again a little bit more like s orbitals. We focus very heavily on carbon when talking about hybridisation, but a logical question to ask is whether other elements found in organic molecules can too have hybridised orbitals. And the answer is yes, they can. To explore this a little bit, let's go back to the ammonia molecule that was drawn in the previous video. So the nitrogen makes 3 bonds, 1 with each hydrogen. That's 6 electrons in total. You will, however, have worked out that to complete the octet there are 2 electrons left over. Now these are not involved in the bonding. They belong to the nitrogen in quotation marks. Because of this, they are known as a lone pair rather than a bonding pair. The concept of lone pairs is very, very important in organic chemistry and in biochemistry. In organic chemistry, reaction mechanisms, they are often drawn as seen on the right, just as 2 little dots representing that different pair of electrons. Elements in group 15 of the periodic table, nitrogen and phosphorus are the common ones that you'll encounter, have 1 lone pair and make 3 covalent bonds to complete their octets. Elements in group 16, common ones are oxygen and sulfur, have 2 lone pairs and make 2 covalent bonds. Elements in group 17, the halogens, have 3 lone pairs and make just 1 covalent bond. And again, these are all fundamental facts that dictate the shapes and structures of organic molecules. You need to know them and remember them. Now, as I've said, lone pairs have important functions, particularly in chemical reactions and interactions between molecules. But for the purposes of determining hybridisation, there's a very simple method for using them to determine the molecular orbital hybridisation of most atoms within an organic molecule. And I've written out the process here. So for any given atom, first count the number of other atoms it's bonded to, then count the number of lone pairs it's going to have, remembering the rules from the previous slide for group 15, 16 and 17 elements, and then just add the 2 numbers together. So when your answer equals 1, that's impossible. If the answer you arrive at is 1, you've done something wrong in your thinking. If the number is 2, the atom's going to be sp hybridized. If the number is 3, it's going to be sp2 hybridized, and if it's 4, it's going to be sp3 hybridized. Using this method, you can work out hybridization for any common element that you'll come across within an organic molecule. You can also do it by looking at the number of double and triple bonds that the given atom is part of. If the atom partakes in single bonds only, then it's sp3 hybridized. If there's 1 double bond there, it's sp2 hybridized. If there's 1 triple bond, or in very, very rare cases 2 double bonds, then the atom is sp hybridized. But a warning, this rule only works for neutral uncharged atoms, okay? And in common organic molecules, the atoms, particularly the heteroatoms, the non-carbon atoms, they often are charged in kind of standard conditions, biological conditions. In some organic reactions, for example, carbons can become positively charged temporarily. And these carbocations, as they are called, so cation meaning a positively charged ion, these carbocations can form 3 single bonds to other atoms, and they are sp2 hybridized because of their charge. So here's a challenge for you. So pause the video here and have a go at this practice problem. Using either of the methods that we've just covered, I want you to try and determine what the hybridization is of both of the atoms highlighted in blue. So the carbon in the middle and the oxygen on the right hand side. So pause the video now, have a think about that, and then resume when you're ready. So here's the answer to that practice problem. For our carbon in the middle, carbons have 0 lone pairs, so we don't have to worry about those. But this carbon has 2 double bonds coming off it, which equates to sp hybridisation. So bonded to only 2 other elements, 2 double bonds equals sp hybridisation. Our oxygen here is bonded, as many oxygens tend to be in organic chemistry, bonded to 2 other elements, a carbon on its left and a hydrogen on its right. But of course the oxygen has 2 lone pairs, so the simple mathematics to do is 2 plus 2 equals 4 equals sp3 hybridisation. So that's the way to do it. You can, if you want more practice, you can just look a little bit further at this molecule and have a look at have a go at determining the hybridisation for the other carbons that exist within the molecule. And that brings us to the end of the video. I hope you've enjoyed it. So just a recap here of the learning objectives that I hope you agree we've covered. There are again plenty of practice problems to have a go at on this material to make sure that you've understood the learning. If you're watching the video around the time when it was first released, you can come along to the workshop session that we're going to hold to practice and get extra advice from one of the instructors. If you're watching this after the workshops have finished, perhaps during an exam revision session, you can access copies of the practice questions and answers using the links provided below the video. Thank you for watching.